Gracias. Good morning, ladies and gentlemen. I'd like to thank the organizing committee of Argentina Mining 2010 for inviting our company to make this presentation. The title is New Analytical Horizons in Copper Gold Exploration. What we intend to look at is, first, the overview. Take a look at the status of greenfields exploration in mining today, the need for renewed greenfields exploration, and what laboratories can do in helping this out through sample media and sample preparation schemes, new ones, as well as new digestion schemes and instrumental analysis. So global mining is facing a downwards spiral in finding new economic ore reserves, despite record exploration expenditures over the past decade. Now, part of this problem is that there are bright spots, such as Argentina, but in more mature mining regions, such as Canada, the trend is unmistakable. The following graphs look at some of the contained mineable ore still existing in Canada. And what you see is a tremendous drop in mineable ore. This first one presents copper from a high of almost 18 million tons of copper in 1983. This has been reduced down to about 6 million tons today. But we see the same thing in other metals. Nickel, a 46% drop. Zinc, a 73% drop. Lead, a 90% drop, going from about 10 million tons down to only about 1 million tons existing. And even gold, which saw a resurgence and developing new reserves in the mid-80s and mid-90s, has seen a 42% drop. So what are some of the factors behind this decline? Well, in part, we are living off a shrinking legacy of world-class deposits found at or near surface, or were particularly amenable to exploration schemes that were developed in the late 20th century. New deposits are proving harder to find and more expensive. Evidence for this is seen in the decreasing yield of exploration dollars expended. Now, in this slide, we're looking at exploration dollars expended to look for gold. During the golden years of gold exploration back in the 1960s to 1970s, $1 of exploration recovered $105 worth of gold. Now, in the latest decade, from the year 2000 to 2009, $1 of exploration found only $11 worth of gold. So what are some of the factors behind this decline? Well, major companies have become more reliant upon replenishing their reserves by being acquisitionists as opposed to being explorationists, particularly in greenfields. Junior intermediate companies are more overly sensitive to the venture markets and thus avoid risk, especially in downturns, and by focusing more on brownfields exploration. Here is a slide from the MEG, which looks at the different forms of expenditure from 1992 to the year 2008, and you can see the unmistakable slide in grassroots exploration, particularly by the majors. So demand for commodities will increase. Forecasted high single-digit growth in the large population developing nations such as China, India, Brazil, and Indonesia will place increasing demand upon commodities. China officially surpassed Japan as the world's second largest economy in August of 2010, just this past month. And at current rates, China is projected to exceed the U.S. as the largest economy by the year 2030 or sooner. This is from The Economist in August 2010. There we go. All right, this is a somewhat older slide that takes a look at the demand for copper. And what it shows is that from the year 2005 to the year 2030, we will require to mine the same amount of copper that has been mined in all of history prior to 2005. So basically, all the metal has been pulled out of the ground up to 2005. We will need to find deposits of those metals in copper to be able to satisfy demand going up to the year 2030. So what can be done to reverse the decline? In the words of John Horonsky, in his presentation to the SEG in 2009, what we need is a greenfield renaissance. And this will be brought on by innovative science and technology that will be the absolute key to find the next generation of greenfield deposits. So what can an assay laboratory do to help? Well, one thing we can do is we can provide highly versatile analytical packages that increase the chances for exploration success. What makes a versatile package? Well, for one thing, we build in maximum flexibility into all stages of the analysis. And I'm going to use here as an example Acme's package group 1FMS. Now, every analytical package basically consists of 3 different stages. And so the first stage is preparation of the sample and the type of sample media you can use. The next stage is the digestion and how you can tweak the digestion to be able to be most accommodating for the greatest number of elements. And finally, the analysis, the actual instrument that generates the data that you're looking for. Acme Labs has worked hard to try to maximize each one of these stages by developing multimedia applications in the preparation stage, by optimizing the digestion, and also by introducing robust instrumentation to be able to deliver the greatest number of elements over a broad concentration range. So looking at the preparation, now the best sample medium is basically an optimum compromise between practicality and representativity. And the typical types of samples we would see are rocks and drill core for late stage development, or soils and sediments for early stage reconnaissance style work. Less common media and their derivatives can discern subtle or hidden anomalies that are due to ore. And some of these materials can consist of vegetation or the ash which is derived from vegetation, as well as clay and other mineral separates. A versatile analytical package can accommodate a very wide range of sample media and concentrations. So looking at just one of these media, clay and the separations that you can form, this is something that our laboratory has worked on extensively just recently. It's part of our research development. The bulk of material in soil and sediment comprise common silicates that really are of no interest. They really don't contain the metal that you're looking for and really just dilute the signal that you're looking for. By analyzing a specific substrate, such as clay, you can maximize the signal. And so here we see one of our technicians actually working with a clay sample. We produce a slurry, we drop out the heavy fraction, basically everything that's larger than 2 microns. And then what we do is we put this fraction, this solution, into a high-speed centrifuge to be able to extract the clay fraction. Now this is a case study of actually using clay fractions. This comes from central British Columbia. It's a porphyry environment. The map you're looking at has a scale of about 120 kilometers north-south by about 60 kilometers east-west. And it represents about 500 samples, which are collected in an area of about 4,000 square kilometers. This work was done in 1995. It was analyzed for a broad range of elements, and the color patterns you see are basically the anomalous samples. The yellow dots in through this area are the trace of the porphyry systems. And there's actually 2 mines in this area. This area was glaciated in the last glaciation, and the glaciers ran from northwest to southeast. And so all the orange patterns you see over here are the copper anomalies, and these are found down ice of the copper showings, which is a good thing to see. They went back and they sent the samples to us for retreatment. They took the archive samples and we reanalyzed them, but first we did a clay separation. What we see is we see the maps that were produced from this. Now, down here we found new copper showings brought up by the copper that was found in the clay fraction. Up here we found new molybdenum showings due to the molybdenum that was found in the clay separations. Now this had not been seen in the original survey. Something else that we've been working on is actually something called lithocards. And what we do is we're looking at the coarse fraction which are contained within these samples, within soil samples and stream sediments. Now very often when clients send us these samples, this material is just screened out and it's tossed away. Yet it provides valuable geological material. And I mean, the client, when they're collecting these samples, may spend thousands, tens of dollars to thousands of dollars per sample to collect these. And so these rock fragments can actually form a geological record which may tell you about the lithology, the alteration, or the mineralization found within an environment. Here we're looking at a close-up of one of these particular lithocards. And in it is a piece of gossan that we extracted from the sample. And this is done when you might have a high response coming from one sample. You can actually tell the laboratory, look, save the coarse fraction, I may want to look at this afterwards, and we can produce these cards. Looking at the digestion, what would be an ideal leach? Well, it's one that's not too weak and not too strong. We call this the Goldilocks paradox. The Acme Labs uses a modified aquaregia digestion, which is a mixture of hydrochloric acid, nitric acid, and water. And it's good for effectively extracting all of the native metals which may be found within a sample, such as gold, silver, platinum, palladium, and so on. But also it can digest sulfates, sulfides, carbonates, phosphates, but it largely ignores silicates. Now, we also introduce a flexibility by giving various options for the sample size. Most laboratories, when they do analysis like this, multi-element analysis, will give you a 0.5 gram digestion, and you can actually sample at the very bottom of the test tube. It's about the size of your fingernail. However, we introduced a large sample digestion, going to 15 grams or possibly even 30 grams. Well, why would you want to do this? First of all, a larger sample size can give you quantitative results that can be comparable to fire assay for precious metals such as gold. And we actually looked at this. Over a 2-year study, we collected all the analyses that we produced by fire assay as well as by looking at gold in our Group 1F package. And we plotted up in this XY graph. The dark black line is the X equals Y line. Basically, any sample plotting on that black line says that the same amount of gold was found in fire assay as compared to the gold reported by this acid digestion Group 1F package. And what you see is that all the samples, or a vast majority of the samples, cluster along that X equals Y line, showing that you get basically comparable results between the two methods. Now, looking at the analysis stage, we want to introduce robust instrumentation. And part of the reason why is that you want to be able to look at as many elements and as low detection limits as possible. In most prospective mineralized terrains where you may be operating, very often these terrains will be endowed by more than one style of mineralization. For example, if you're looking at a copper terrain, porphyry copper terrain, you also have the opportunity to find epithermal gold and silver, whether it be high sulfidation or low sulfidation systems. You also have mesothermal gold and silver with base metals, or possibility of base metal or of skarns hosting gold, copper, and possibly tungsten and other elements. This is just a schematic of a simple porphyry system. I'm sure you're all familiar with this, with the mineralization of potential for a copper mineralization near the base, skarns off to the right, and then high sulfidation and low sulfidation gold systems. Other places, Archean greenstone belts. Well, Archean greenstone belts are very prospective for looking at gold, particularly shear-hosted mesothermal as well as banded iron formation gold. However, these are also very prospective terrains for looking at volcanogenic massive sulfide deposits, such as lead, zinc, and copper. Also, they can host komatiite magmatic deposits of nickel and copper, as well as PGEs. Now, a robust instrumentation scheme provides, first of all, multi-element capability for primary commodity as well as associated pathfinder elements found in most deposit types. And I refer to this as planned serendipity. In other words, planning to find something that you're not looking for. Also provides detection limits from the ultra-low end to near ore grade, thus ensuring that background of any type of rock or any type of material you're sampling is truly seen. And by seeing the background, you can know what's anomalous. So Acme Labs Group 1F package uses both the ICP-ES instrument and ICP-MS instrument integrated through our Acme InSync technology to deliver all of the above. So looking at one of the instruments, the ICP mass emission spec, what does it do? Well, basically it measures light. It uses a high temperature plasma that when the sample goes through, it produces light. The light passes through a refraction grating, and basically it produces wavelengths, each wavelength corresponding to an element, and this hits a detector. The higher the intensity of the wavelength, the higher the concentration of that particular element. We also use ICP mass spec, and ICP mass spec also uses a high temperature plasma. With the sample entering into the plasma, it produces a trail of ions that pass into a filter, a quadrupole filter. That filter basically sends out all the elements that's not interested in and only allowing the element of interest to actually hit the detector. So you're actually counting atoms of the element of interest. Now here is just a periodic table. In a good versatile package, you'll be able to provide quite a variety of elements. And so here we see, well, in the Group 1F package, we offer a basic suite of 37 elements, which comprise precious metals such as silver and gold, as well as trace metal, or I should say the transition metals, base metals, as well as a number of interesting pathfinder elements, and some also interesting energy elements, as well as rare earths. In the extended version of this package, we provide an additional 14 elements off the same digestion through the same analysis, which includes more precious metals, palladium and platinum, as well as some more interesting trace pathfinder elements, and more rare earths. We can actually add on the complete series of rare earth elements into this package. Now, what would it be useful for? Well, looking at a number of different styles of deposits, looking at both the metals which are found in the deposit as well as those which can act as pathfinders, we see that for high sulfidation epithermal deposits, the metals of interest, of course, being gold, silver, copper, and also the pathfinders, all these are available in the base package. Low sulfidation systems, most elements are available in the base package, as well as introducing lithium, rubidium, and cesium, which are available in the extended package. Porphyry systems, again, most elements are available in the base package, but some porphyry systems can also contain palladium and platinum. This is available in the extended package. Skarn deposits, most elements that you would look for. Iron oxide, copper, gold, the elements of interest. VMS deposits, various sources for base metals, SEDEX deposits, Mississippi Valley type deposits. Most of these are available in the various packages that are offered in this analytical scheme. Uranium deposits. Now, this is something that we've been working on recently, doing research with another company. And what we've been working on is actually looking at isotopes of lead. And by using the isotopes of lead and calibrating to these, we can actually distinguish a radiogenic lead signature from a natural lead signature. And this can be looked at a number of different materials. Kimberlite deposits, looking for diamonds. We can use a suite of elements, including the rare earths, to be able to identify traces for these kimberlites. Now, here's actually a good example of that. This is from a client of ours, GGL Diamond Corp, and they were looking for diamonds up in the Northwest Territories of Canada. They were running these, collecting samples of till, and they were running just these orientation lines going across the countryside. Now, on one of these orientation lines, they happened to hit coincident nickel and copper in this area. And this, of course, was an interesting signature to them. So they went out prospecting in this area, and very shortly they found basically nickel-copper magmatic mineralization in an outcrop. Drilling of this outcrop, it resulted in 5.1 meters of 1.73% nickel and 1.7% copper. Massive nickel-copper mineralization. Now, looking at detection limits, where can this benefit? Well, in a package such as this, we can produce very low concentrations, reportable and reproducible low concentrations of gold down to about 0.2 ppb, as well as silver down to 2 ppb. Now, most deposits I've encountered actually do contain silver as an associate metal, and being able to look at silver down to 2 ppb makes a very powerful pathfinder. The package also includes mercury down to about 5 ppb. So looking at a case study where this has been beneficial, this is from the Géologie Québec. A fellow who gave this to me is Marc Baumier, who conducted a survey in an area where there is known Carlin-style gold deposits. This is from, they did a survey back in 1965 where they collected stream sediments and analyzed these using the technology of the day, which was atomic absorption. And what they found was that they saw no trace of the Carlin deposits in the stream sediments, even though one sample was collected basically just downslope, immediately downslope of the deposit. The deposits are these purple stars which don't show up too well. So they sent the samples off to us. They had these samples in archive, and they sent it off to us for analysis, and we analyzed it with our Group 1F package. The resulting map that came out of it provided a trace of metal of gold that could be seen for up to 2 kilometers downstream. When they did the analysis, what they found was that the background in the area was about 0.3 ppb gold, and that the highest value they found immediately downslope of the deposit was 5 ppb gold. Now, that basically, it couldn't be seen by the old technology because it was below the detection limit. But by a method like this, it was quite discernible. So in conclusion, selecting an analytical package that enhances rather than limits is integral to planning for success in greenfields exploration. A versatile package like the Group 1F provides flexibility in sample media, optimal digestion for most elements, selectivity in the sample size, element suites for all deposit types, as well as unparalleled detection limits. And I'd like to just thank the various contributors to this presentation for giving me their case studies. Marc Bonnet from Géologie Québec, Travis Furby from BC Geological Survey, Ray Herkus from GJL Diamond Corp. Thank you.